When NATO began evaluating next-generation fighter engines in the late Cold War era, every major power expected one thing. The new standard would likely come from either the United States or an existing European giant. Sweden, with its smaller aerospace industry, was not expected to challenge this assumption, especially when earlier Scandinavian jets used Volvo-based power plants. But behind the scenes, a quiet revolution was forming. Rolls-Royce, already a legendary name in military propulsion, decided that the next chapter of European air power would not be written by Volvo Aero. Instead, they aimed to build an engine precise enough, powerful enough, and adaptable enough to become the favorite of NATO planners. The result was a bold partnership, a radical redesign of core systems, and a technology leap that changed the fate of an entire fighter program. It all started with a simple requirement. NATO wanted an engine that could fit inside a compact airframe, deliver high thrust at low weight, operate in Arctic winters as easily as Mediterranean summers, and still meet strict cost and maintenance demands. The requirement sheet looked impossible, and most engineers said the combination of thrust to weight, fuel efficiency, and reliability could not coexist. But Rolls-Royce did not see a contradiction. They saw an opportunity. They began studying the older GE F404 architecture, but realized the original design could be pushed far further than anyone imagined. What Volvo wanted was a licensed-built version, something conservative and safe. What Rolls-Royce wanted was a re-engineered European variant built for extremes. NATO officials were immediately attracted to Rolls-Royce's engineering philosophy. Instead of creating a new engine from scratch, they enhanced an already proven platform and then rebuilt its weaknesses. Everything from the high-pressure compressor geometry to turbine cooling, digital engine control, and exhaust shaping was rethought. They were not competing with Volvo. They were out-innovating them. And the numbers were shocking. Rolls-Royce offered an engine that maintained thrust even during brutal high-angle maneuvers, something essential for the kind of dogfights NATO still prepared for. During cold weather trials, the engine demonstrated flawless starts even at extreme sub-zero temperatures. Where older engines choked on ice crystals, this one performed like a machine designed for the Arctic. Engineers from multiple countries quietly admitted that Rolls-Royce had achieved what seemed mechanically impossible: high stability at low weight. Sweden's own defense ministry was stunned. Their Gripen program needed a power plant that could launch from short rural roads, accelerate fast enough to survive missile-rich skies, and do so with far lower operational costs than an American stealth jet. Rolls-Royce showed them simulation after simulation, proving that their enhanced engine, later known as the RM-12, could support violent throttle changes, prevent compressor stalls, and stay safe even if a bird was sucked into the intake, something many NATO jets had struggled with. By the time the early prototypes ran on test stands, the international engineering panels realized Rolls-Royce was not just supplying an engine. They were rewriting the rulebook for European fighter reliability. But the deeper story of why Rolls-Royce won and Volvo did not lies in the politics and the physics of propulsion development. Volvo Aero was a respected company with strong regional influence. Yet NATO required a partner capable of meeting global high-risk military demands. Rolls-Royce had a century of experience with high-temperature alloys, afterburner tuning, and compressor blade aerodynamics, something that takes generations to perfect. When NATO looked at long-term support, deployment cycles, and multinational interoperability, they wanted an engine backed by an industrial ecosystem that could sustain upgrades for decades. Rolls-Royce fit that requirement naturally. They had teams that specialized in fatigue testing, thermal stress modeling, and battlefield-grade fault-tolerance systems. This depth allowed them to promise something Volvo simply could not: an engine optimized for extreme reliability under combat loads. The engineers also introduced a radical safety system, a strengthened fan module that could survive catastrophic bird strikes without causing the entire engine to disintegrate. NATO air bases had reported multiple incidents involving birds, small animals, and runway debris damaging engines across Europe. Rolls-Royce decided to build an engine that could take a hit and keep flying. They conducted destructive testing where they fired gel-based impact materials directly into the blades at high velocity. While most engines would fail, the reinforced RM-12 design maintained containment. This instantly placed the engine in a different category. A fighter like Gripen, which would operate from highway strips, needed that level of protection. NATO evaluators quietly noted that the Rolls-Royce version offered battlefield resilience unmatched in its weight class. Then came digital control. Rolls-Royce integrated a modern FADEC system, full authority digital engine control, which allowed the pilot to push the engine to its limits without worrying about airflow surges or thermal spikes. Instead of relying on manual throttle discipline, the FADEC continuously calculated pressure ratios, fuel flow, and turbine temperature in milliseconds. This gave Gripen pilots an edge. They could maneuver aggressively, change altitude rapidly, and demand instant thrust, all while the computer kept the engine stable. NATO's test pilots loved this. They reported that the aircraft felt alive, responding with the precision of a sports car rather than a complicated jet. The Rolls-Royce FADEC turned the R-12 into an extension of the pilot's instincts. At the same time, Rolls-Royce fought to keep operating costs low. They introduced modular construction, meaning entire sections of the engine could be swapped in the field without major disassembly. This was a breakthrough for small air forces that could not afford giant hangars or long maintenance downtime. Sweden demonstrated that their technicians could remove the engine, inspect it, and reinstall it within hours, not days. NATO logistics teams realized the strategic advantage. An air force using this engine could keep jets flying during wartime when supply chains were under attack. Volvo's proposals lacked this level of service-based engineering. Rolls-Royce understood both warfighter needs and long-term sustainment, which allowed their design to dominate NATO's evaluations. The geopolitical climate added its own momentum. As NATO looked to integrate European manufacturing more tightly, the idea of combining British precision metallurgy with American baseline design made the RM-12 a symbol of transatlantic cooperation. Many American advisors appreciated that Rolls-Royce did not try to replace the GE lineage, but enhanced it. This created a smooth certification pipeline, lowering risks. Meanwhile, Sweden realized that adopting this power plant would open doors for future exports. Since the engine was co-developed with major Western partners, buyers would trust its reliability. Rolls-Royce's global reputation essentially guaranteed long-term parts availability, making Gripen far more attractive internationally. Behind every decision was a simple truth. Volvo Aero had competence, but Rolls-Royce had mastery. And mastery is what NATO needed. The moment that sealed the engine's future came during a series of brutal demonstration flights. Test pilots were ordered to push the prototype jet in ways that would normally risk compressor stall, sudden throttle blasts, high G turns, rapid altitude changes, and high-angle nose-up climbs. The RM-12 behaved flawlessly. Even when it hit turbulent pockets known to disturb airflow, the pressure stability held. Engineers watching the telemetry streams were stunned to see turbine temperatures staying within safe bands, despite aggressive afterburner cycles. What Rolls-Royce had built was not just a variant, it was a re-engineered machine adapted for a modern European battlefield. The engine could handle snow ingestion, ice, rain, debris, and high-heat runways in the Middle East. This environmental flexibility became one of NATO's strongest arguments for adopting it. Another major milestone came during endurance testing. Rolls-Royce ran the engine non-stop at high power for hundreds of hours to simulate wartime operations. Many engines lose efficiency or show micro-fractures after prolonged stress. The RM-12 retained stability, and the wear patterns were minimal. When metallurgists inspected the blades, they found no early-stage fatigue beyond expected margins. This meant the engine had decades of service life baked into its design. For NATO planners who needed reliable air defense capability in Europe's northern regions, where bases were widely dispersed, the 12E's longevity was a massive advantage. The more the alliance evaluated the numbers, the more obvious it became that Rolls-Royce had delivered something exceptional. Sweden's entire Gripen program evolved around this reliable thrust source. The aircraft's famous ability to launch from 800-meter road strips, turn around in 10 minutes, and take off again depended heavily on an engine that could handle rapid cycles. Ground crews could operate with minimal tools because the engine was designed for practicality. Rolls-Royce had effectively created a pilot-friendly, technician-friendly, budget-friendly powerhouse. And as defense budgets tightened, this mattered more than ever. NATO analysts realized that many smaller air forces could afford Gripen because the engine kept running costs low. Fuel efficiency was impressive, Maintenance cycles were long and spare parts were easy to source globally. Then export deals began reflecting the engine's success. Countries comparing Gripen to American or Russian fighters noticed something crucial. The RN-12 engine required fewer man-hours per flight hour. This translated into millions saved annually. Even nations with heated climates saw the benefits. The engine handled high-temperature takeoffs without thermal instability. Meanwhile, pilots consistently praised its throttle response and forgiveness during violent maneuvers. It gave them confidence, a psychological advantage that cannot be bought. As more nations ran evaluations, the story spread. Rolls-Royce had refined a platform once considered modest into a world-class propulsion system. NATO's final endorsement carried symbolic weight. For decades, large American manufacturers dominated engine decisions. Yet here, a European-American hybrid win emerged. The alliance recognized the RM-12 as a triumph of engineering pragmatism. Not the most powerful engine in the world, not the most complex, but the most balanced, reliable, and adaptable for real combat scenarios. And this is why the narrative shifted. It was not Volvo that shaped the engine NATO trusted. It was Rolls-Royce. Their work transformed Gripen from a regional experiment into a globally respected fighter platform. The legacy continues today. Every time a Gripen takes off from a small highway in Sweden, a remote base in Hungary, or a coastal airstrip in Brazil, the RM-12 engine roars with a design philosophy that prioritizes survival, affordability, and pilot control. Rolls-Royce proved that innovation does not always mean reinventing everything. It often means perfecting what already works. In doing so, they built the engine NATO wanted, and they wrote themselves into the story of modern air power, ensuring that their engineering legacy lives on with every sortie, every scramble, and every mission where reliability determines victory.